convoluted tubule. We have a little bit. Now, when you block carbonic anhydrase, what is going to be the primary result from blocking carbonic anhydrase? That's right, Maria. So it means it'll decrease reabsorption of bicarb, causing bicarbonaturia, and of course, metabolic acidosis. So of course, I'm looking at this, and most of us went for answer B, an increased serum anion gap, metabolic acidosis. However, it's wrong because it will be with a normal serum anion gap. Why is it going to be a normal serum anion gap? Because of this, there will be hyperchloremia when you block reabsorption of bicarb. Less bicarb in means less chloride out. Bicarb and chloride always exchange for each other. So, of course, that's what normalizes the serum anion gap. Now, there won't be hyperkalemia because there's going to be loss of salt and water. It's a diuretic. There's going to be secondary increase in aldosterone. And the secondary increase in aldosterone is going to cause potassium wasting. And finally, when you damage a PCT function, when you damage a PCT function, means less phosphate retained. So you generally see hypophosphatemia. Even in chronic setting like RTA type 2, you might even get hypophosphatemic rickets from this. Your urine anion gap, on the other hand, is going to be negative as you increase proton excretion as ammonium chloride. So I have to explain to you this one now, but let's look at this then together. And first thing we're going to do is let's talk about the serum anion gap. To calculate the serum anion gap, what is it all about? Basically, it's about electroneutrality. That's all it is. Electroneutrality is simply telling you that if these represent cations, then they must be equal in amount to dog ions. Oops, no, to anions. If there's cations, there has to be dog ions somewhere. Cations and anions must always equal one another. It's a principle of electroneutrality. Now, in ECF, in blood, the main cation by far is primarily sodium, which is around 135 to 145, so around 140 milliequivalent per liter. Oh, there's a little bit of potassium. It's around 3.5 to 5 or so, so, you know, around 4, 5 milliequivalent per liter. And there are others too that are even less than this. For the anion, a big anion is chloride, but chloride is anywhere between 96 and 106, so around 100 milliequivalent per liter. And certainly there's bicarb, which is around 24 milliequivalent per liter. And there's some others that are not measured. And these others that are not measured, that's the gap. Okay, that's the anion gap. So when we calculate the serum anion gap, generally we take sodium, we don't even take potassium, some people do, and we remove to it chloride plus bicarb. And imagine 140 minus 124, then here it would be around 16. So anything that's from 3 to 17 is normal. So a normal anion gap could be 10, could be 12 milliequivalent per liter. So remember, it's all about electroneutrality. In acidosis, if it's metabolic, decrease bicarb must be met by increased other anions to maintain electroneutrality. It could be increase not measured ones. Example, lactate. Example, beta hydroxybutyrate, acetoacetate, maybe oxalate from ethylene glycol, maybe formate from methanol, you know, etc. with an 8. Salicylate, for example. And if that's the case, this would cause an increased serum anion gap. The other possibility is it could be matched by an increase in chloride, which is measured. And when you do sodium minus an increased chloride plus a decreased bicarb from the metabolic acidosis, then what is it that's not going to happen? If your drop in bicarb was matched by an increase in chloride to keep electroneutrality, then obviously what is not going to happen to the serum anion gap? That's right. There'll be no change in the serum anion gap. So that it allows you to split metabolic acidosis in two big families. The ones where the low bicarb is associated with elevation of an anion that we don't measure, so it increases the serum anion gap, or the one where the anion that is increased happens to be chloride, then we call it a hyperchloremic metabolic acidosis, and in that setting, there would be no change in the serum anion gap. Is that okay? You understand that it's all based on electroneutrality? Sharon, are you still here? You understand the serum anion gap right now? So anytime bicarb drops, it must be met by other anion offsetting the drop in bicarb. If it's chloride, there's no change in serum anion gap. If it's due to other weak acidic compound like lactate